Welcome to today's class. In this class, we'll be discussing the topic Derivations of Half Wave Rectifier Circuits. In this topic, we are going to look at the various expressions that are used in analyzing half wave rectifier circuits. We are going to be deriving most of these expressions. So let us begin by deriving the average output voltage, Vout average, of the diode. The Vout average of the diode used in a half wave rectifier circuit is given as Vout average is equal to 1 over 2 pi, integrating from 0 to pi, Vout the omega t. That's equal to 1 over 2 pi, integrating from 0 to pi, Vm sine omega t d omega t, and that will be equal to Vm over 2 pi minus cos omega t 0 to pi. Of course, if we integrate sine omega t d omega t, it will give us minus cos omega t. So if we substitute the limits, we have Vm over 2 pi into minus cos pi minus cos 0, and we know that cos pi is equal to minus 1 and cos 0 is 1. So substituting these values, we'll have Vm over 2 pi into 1 plus 1. That gives us 2Vm over 2 pi, which is Vm over pi, and that's equal to 0.31 Vm. So we have that Vout average is equal to Vm over pi, or 0.318 Vm. We'll call this equation 1. So that's the first equation we're deriving for the half wave rectifier. Now let us look at the average load current. The average load current Iout average giving us Vout average over RL. That is substituting for Vout average, which is Vm all over pi, then RL. So that gives us 0.318 Vm all over RL. I'll call this equation 2. Now let's derive the expression for the RMS output voltage. The RMS output voltage is given as Vout RMS is equal to the square root of 1 over 2 pi, integrating from 0 to pi, Vout square d omega t, and that is equal to 1 over 2 pi, integrating from 0 to pi, Vm square sine square omega t d omega t raised to power 1 over 2. Of course, recall that Vout is equal to Vm sine omega t, so we are simply substituting for Vout, which is Vm sine omega t. So since we are looking at the square of Vout, simply Vm square sine square omega t. But sine square omega t is equal to 1 over 2 into 1 minus cos 2 omega t. So if we put that in place of sine square omega t, we are going to have Vm square over 2 pi, integrating from 0 to pi, 1 over 2 into 1 minus cos 2 omega t d omega t. Of course, that's raised to power 1 over 2, and that will give us Vm square over 2 pi omega t over 2 minus sine 2 omega t over 4 pi 0, which are the limits, raised to power 1 over 2. And that will be equal to Vm square over 2 pi. Substituting our limits, we have pi over 2 minus sine 2 pi over 4 minus 0 minus sine 0 over 4 raised to power 1 over 2. Of course, sine 2 pi is equal to 0 and sine 0 is equal to 0. So this tends to 0 and this tends to 0. So that will give us Vm square over 2 pi times pi times pi over 2, or raised to power 1 over 2, which is same as Vm square over 4 over 1 over 2, which is Vm over 2, or 0.5 Vm. Our Vout root mean square will be equal to Vm over 2 which is same as 0.5 Vm. I will call that equation 3. Similarly, the RMS load current, which is I at RMS, will be equal to V out RMS over RL. That's Vm over 2RL, or 0.5 Vm over RL. I will call that equation 4. We know that the output voltage from a rectifier is a pulsating voltage, and thus it contains some ripples. The output voltage is simply made up of the output voltage V out average plus the ripple voltage. Now we've already seen the V out average, the average output voltage. Now let us talk about the ripple voltage. So the instantaneous ripple voltage VRO can be expressed as Vs minus V out average, which is Vm sine omega t minus V out average for 0 less than or equal to omega t less than or equal to pi, or minus V out average for pi less than or equal to omega t less than or equal to 2 pi. So that is the instantaneous ripple voltage VRO. So the RMS ripple voltage VRMS is simply giving us the RMS ripple voltage VRMS can be given as VRMS square plus V out average square is equal to V out RMS square. And so V ripple RMS square will be equal to V out RMS square minus V out average square. Okay, earlier on we've seen the instantaneous ripple voltage VRO, and the instantaneous voltage VRO is given as this expression. So we'll call this expression equation 5, and now the V ripple RMS square, we'll call that equation 6. So if we express the V out RMS in terms of V out average, we're going to have, substituting our equation 1 and equation 3 into equation 6. Recall that equation 1 is V out average is equal to Vm over pi, and that gives us Vm is equal to pi V out average. And we also recall that V out RMS is Vm over 2. So if we substitute the expression for Vm from equation 1 into this equation, we have it has been equal to pi V out average over 2. So our V arrow root mean square will be equal to pi over 2 V out average square minus V out average square, and that gives us pi square over 4 V out average square minus V out average square. And so our V ripple root mean square will be given as pi square over 4 V out average square minus V out average square raised to power 1 over 2, or the square root of that, which gives us V out average into pi square over 4 minus 1 raised to power 1 over 2. That gives us 1.21 V out average. So that means the ripple voltage, the root mean square ripple voltage, is giving us 1.21 V out. I will call that equation 7. The ripple factor RF is giving us VR root mean square over V out average. That's 1.21 V out average over V out average, which is 1.21 or 121%. We'll call that equation 8. So the ripple factor for a half wave rectifier is 121%. That is a single phase half wave rectifier. Now the AC output power, P at AC, is the average power and is giving us 1 over 2 pi integrating from 0 to 2 pi I at square RL d omega t. And that gives us 1 over 2 pi I at RMS square RL omega t 0 to 2 pi, which is same as 1 over 2 pi I at RMS square RL 2 pi minus 0, which is same as I at RMS square RL So our P out AC output power, P out AC, is equal to I out ROMS square RL, or V out ROMS times I out ROMS, or V out ROMS square over RL, which is same as VM all over 2 square times 1 over RL. We call this equation 9. If there are no power loss in the rectifier, it simply means that the input power, assuming no power loss, will be equal to the output power, which is Vm all over 2 square times 1 over RL. I'll call that equation 10. Next, let's derive the expression for the DC output power. The DC output power, P out DC, is given as V out average times I out average, which is equal to V out square average over RL, and that's the same as Vm all over pi all square times 1 over RL. We call that equation 11. P out DC is usually smaller than the P out AC, since the RMS values are larger than the average DC value. So if the output DC power is usually smaller than the output AC power. So let us look at the rectification efficiency. The rectification efficiency will be given as the output DC power over the output AC power. That is V out average times I out average divided by V out root mean square times I out root mean square. So that gives us Vm all over pi all square times 1 over RL all over Vm over 2 all square times 1 over RL. That gives us 4 over pi square, which is equal to 40.5%. We call this equation 12. So the rectification efficiency of a half-wave rectifier is equal to 40.5%. Assuming there are no power loss, we'll get the input power has been equal to Vs Is power factor has been equal to the AC output power. So the power factor will simply be equal to the AC output power over Vs Is, and that will give us Vm over 2 square times 1 over RL over Vm over root 2 times Vm over 2 RL. And if we simplify that, we're going to have root 2 over 2, which is same as 0.707. We call this equation 13. So the power factor for a half-wave rectifier is given as 0.707. So these are the expressions that we use in calculating or analyzing a half-wave rectifier. So what have we learned in today's class? So in this class, we have derived 13 expressions or equations that can be used to analyze or solve problems in half-wave rectifier. We have seen the output voltage, the output average voltage given as equation 1, the output average current given as equation 2, where I out average is equal to 0.318 Vm all over RL. And then we've also seen the expression for the output RMS voltage given as Vm over 2 or 0.5 Vm. Similarly, the output RMS current is given as 0.5 Vm over RL. And then went ahead to derive the expression for the RMS ripple voltage. The RMS ripple voltage, we saw that it is given as 1.21 V out average, and then the ripple factor is 121% for a single phase half-wave rectifier. We equally derived the expression for the output AC power, and we saw that the expression for the output AC power is I square RMS RL. And then we also assume that the input power is equal to the output power. And if that is the case, then the input power Vm over 2 square times 1 all over RL. And then we derive expression 2 for the output DC power. The output DC power is given as Vm all over pi square times 1 over RL. And then we got the expression for the rectification efficiency. The rectification efficiency for a single phase half-wave rectifier is simply 14.5%. And finally, we derive the expression for the power factor. And the power factor for a single phase half wave rectifier give us 0.707. In subsequent class, we are going to solve some problems of half wave rectifier and see how these analysis or these equations we just derived can assist us in solving those problems. So that is all for this class. See you in our next class.